Hey, what's up everyone? Welcome back to the channel. If you're watching this, chances are you're either preparing for the Snowflake SnowPro Core Certification Exam, or you're just trying to level up your Snowflake knowledge in general. Either reason is a great one to be here. A quick note before we dive in. For each question, I'm going to read through the scenario, walk you through all the options, and give you a moment to think. Then I'll come back and break down every choice, the right ones and the wrong ones, because honestly, understanding why a wrong answer is wrong is just as powerful as knowing the correct one. All right, let's get into it. Question 1, here we go. So let's look into the first question. And this one is all about Kafka ingestion, something that comes up a lot when you're working with real-time streaming pipelines into Snowflake. Here's the scenario. A Snowflake architect is evaluating ingestion reliability for a Snowflake connector for Kafka deployment. The architect wants to understand how Kafka records are stored when they land inside Snowflake. And the question is simply this: which statement accurately describes the ingested data format? Now picture this. You've got a Kafka cluster pumping messages, events, logs, transactions, whatever it is, through the Snowflake Kafka connector and into a landing table. The architect runs a quick des table command and sees two columns come back: record metadata and record content. Then they fire off a select to look at an actual row. Here are your four options. Take a moment and think about what you know. Option A, each record is stored in a single variant column. Option B, each record is stored in binary compressed format. Option C, each record is parsed into multiple varchar columns automatically. Option D, each record is mapped into parsed relational columns. Pause if you want, think it through. Which of those feels right to you? Pause the video here, think, and choose the right answer. All right, let's talk about it. So here's the thing about the Snowflake connector for Kafka. It is very intentionally designed not to assume anything about the structure of your messages. Why? Because Kafka is a streaming platform where schemas evolve constantly. One day your message has 5 fields, next day it has 15. If Snowflake tried to parse that into rigid columns, your pipeline would break every time the schema changed upstream. That would be a nightmare. So what does Snowflake actually do? It takes the entire message payload, whether it's JSON or Avro, and stores it in a single variant column called record content. Your metadata, the topic name, the partition, the offset, that goes into another variant column called record metadata. Clean, simple, flexible. That makes option A the correct answer. Each record lands in a single variant column. Now let's quickly understand why the other three are wrong, because they're all tempting in different ways. Option B says binary compressed format. You might be thinking, well, Kafka does use compression, and you're right. Kafka can compress data in transit, but that's transport level compression. Once the data arrives in Snowflake, it's stored logically as a variant. The micropartition compression that Snowflake does at the storage layer is completely transparent. You never see it when you query. So B is confusing transit compression with logical storage format. Option C says parsed into multiple varchar columns automatically. This sounds convenient, right? Like Snowflake would just look at your JSON and create a column for each field, but that would require a predefined schema. Snowflake doesn't do that automatically. If you want that, you have to do it yourself after the data lands, using something like lateral flatten or the colon notation syntax. That's the schema on read model. You decide when and how to parse. And option D, parsed into relational columns, is basically the same trap as C, just worded differently. Relational column mapping doesn't happen at ingest time, period. So the big takeaway from this question is Kafka data lands as variant in Snowflake. That's the schema on read philosophy at work. Downstream transformation is your responsibility, done through SQL after the fact. If you're designing a Kafka to Snowflake pipeline, plan for a flattening layer after the landing table. All right, great start. Let's move to question 2. Question 2 is a bit more operational in flavor, and it's the kind of thing you deal with on a Monday morning when something's gone wrong. I know, not the best scenario, but these are real exam topics and real-world situations. Here's the setup. A Snowflake architect needs to recover failed files from an internal named stage after a load error. The team had created an internal stage, uploaded a CSV file via put, and then tried to load it using copy into. The copy failed. Maybe there was a data format issue, maybe a schema mismatch, and now the architect needs to get that file back from the stage. The question asks, which method requires the least operational overhead? Your options are option A, Snowflake REST API, option B, Python connector download script, option C, get command via SnowSQL, option D, Snowsite Web UI download. What would you pick? Which one feels like the path of least resistance? Pause the video here. Think and choose the right answer. Okay, let's break this down. Now, before I give you the answer, I want you to think about what least operational overhead actually means. It means which of these can you do right now with the fewest steps, the least setup, and no additional code to write or maintain. Option A, the REST API. Look, the REST API is powerful, but getting it set up means dealing with authentication tokens, constructing the right endpoint URL, handling HTTP responses in code. That is not minimal overhead. That's a project. Incorrect. Option B, a Python connector download script. Again, you need to write the script, test it, make sure the connector is installed and configured, handle errors in code. More overhead than we want here. Incorrect. Option D, Snowsite Web UI. This is actually a trap that catches a lot of people because Snowsite is the modern slick UI for Snowflake, and you might assume it can do everything. But here's the thing. Snowsite does not support get operations for internal stages. You literally cannot browse an internal stage and click download. So this option isn't just less ideal, it's not even possible. Incorrect. That leaves us with option C, the get command via SnowSQL, and yes, this is the correct answer. Here's why it's so clean. SnowSQL is Snowflake's command line client, and the get command is specifically built for this exact situation. One line, get at my internal stage /orders 2024.csv files local /recovery path // and you're done. No authentication setup beyond your normal SnowSQL login, no code to write, no dependencies to install. It's purpose-built for retrieving files from internal stages. So the lesson here is really about knowing your tools. SnowSQL's get command is the specialist tool for this job. When you're in an operational pinch and need to recover a file fast, get via SnowSQL is your answer. Keep that in your toolkit. Moving on to question 3. All right, question 3 is about table types in Snowflake, and this is one of those foundational topics that the exam absolutely loves. You're going to see table lifecycle questions come up repeatedly, so let's make sure this clicks. The scenario, a data engineering team creates a temporary table during a session to hold intermediate aggregation results. They're doing things like calculating total quantity and total revenue per product and region, storing that in a temp table called session summary, and then using it downstream to compute average unit price. Standard ETL pattern, right? Pretty common. The session ends, the connection closes. What happens to that temporary table? Your 4 options. Option A, the table is automatically converted to a transient table. Option B, the table is retained and available for time travel. Option C, the table is automatically dropped. Option D, the table persists permanently until explicitly dropped. Take your pick. Pause the video here. Think and choose the right answer. Okay, so this is actually one of those questions where once you know the rule, it clicks instantly. But if you're fuzzy on the table type distinctions, all four of these sound, let me walk through them. The correct answer is option C. The table is automatically dropped. Temporary tables in Snowflake are session scoped. That's the fundamental rule. They exist only for the duration of the session that created them. The moment that session ends, whether it's a graceful disconnect, a timeout, whatever, Snowflake automatically drops the table. No intervention needed, no cleanup script required. This is actually really useful behavior for a few reasons. First, it means you don't have to remember to clean up your scratch tables. Second, it keeps storage costs minimal for intermediate data. Now let's look at why the wrong answers are wrong, because they reveal some important Snowflake nuances. Option A says it converts to a transient table. This is completely made up. It doesn't happen. Snowflake doesn't automatically promote or demote table types. A temp table is born a temp table and dies a temp table when the session closes. Option B says it's retained for time travel. Now this one is genuinely tricky. You might be thinking, well, maybe Snowflake holds onto it just in case. Nope. Temporary tables have zero time travel support. There is no 0 day, no 1 day, nothing. Once that session ends, the data is completely gone. You cannot recover it through any Snowflake mechanism. So if your team relies on time travel for recovery, temporary tables won't save you. Option D says it persists permanently. If that were true, you'd end up with hundreds of orphan scratch tables over time. That would be a mess. Snowflake was designed better than that. Permanent persistence is what permanent or transient tables are for. So here's your cheat sheet for remembering this. Permanent tables, full features, full-time travel up to 90 days. Transient tables, no fail-safe, time travel of 0 to 1 day. Temporary tables, session scoped only, no time travel, no fail-safe, auto-dropped when session ends. Know those three and you'll nail any table lifecycle question on the exam. Question 4 is next, and this one is a multi-select, so stay alert because there might be more than one correct answer. Let's look into question 4, and I want to be upfront with you. This is one of the more nuanced questions in the set. It's testing your knowledge of Snowflake transaction behavior. And there are some rules here that are counterintuitive if you're coming from a traditional SQL background. Here's the setup. A Snowflake developer is writing an ETL stored procedure. They have 3 blocks of SQL to examine. Block 1 shows a transaction using begin work and commit work with some DML inside. Block 2 shows a transaction that includes both a DML statement and a DDL statement, specifically a create table, followed by a rollback. Block 3 shows a stored procedure that tries to run alter session set auto commit equals false inside the procedure body. The question asks, which of the following statements about Snowflake transactions are correct? And remember, select all that apply. This is a multi-select question. Here are your 5 options. Option A, DDL statements implicitly commit any active transaction. Option B, the auto commit parameter can be changed inside a stored procedure. Option C, begin work is a valid syntax to start a transaction. Option D, commit work is a valid syntax to end a transaction. Option E, DDL can safely be included inside an explicit transaction block. Take a moment. Which ones do you think are true? Pause the video here. Think and choose the right answer. Okay, let's work through this. The correct answers are A, C, and D. Let me explain each one. Option A is correct. DDL statements implicitly commit any active transaction. This is the big one, and it's the one that trips people up most often. In Snowflake, if you're inside a transaction and you run any DDL statement, create, alter, drop, truncate, it doesn't just execute that DDL. It also commits everything that came before it. So in block 2 of our scenario, when the create table runs, that insert from before it gets committed immediately, even though we intended to roll back the whole block. The rollback then has nothing left to roll back. This is really important to understand for designing correct ETL pipelines. Option C is correct. Begin work is valid syntax to start a transaction. In Snowflake, you have 3 equivalent ways to start a transaction: begin, begin work, and begin transaction. They all do the same thing. So the begin work you see in block 1 is perfectly valid Snowflake SQL. Option D is correct. Commit work is valid syntax to end a transaction. Similarly, you can end a transaction with commit or commit work. Both are supported. The block 1 example does exactly this. Now let's talk about the incorrect options. Option B is wrong. You cannot change auto commit inside a stored procedure. If you try to run alter session set auto commit equals false inside a stored procedure body, Snowflake will throw an error at runtime. Auto commit is a session level setting that must be configured before the procedure is called. This restriction exists to keep transaction behavior predictable inside procedural code. Option E is wrong, and notice how similar it sounds to option A, but stated as the opposite. DDL cannot safely be included in explicit transactions. If you're inside a begin commit block and you drop a table or create a table, that DDL fires an implicit commit and breaks your transaction's atomicity. You cannot roll it back. So no, DDL inside explicit transactions is not safe. It's a design trap. The big exam takeaway here: DDL auto commits in Snowflake. Full stop. Design your transactions to avoid mixing DDL inside the same transaction block, and don't try to modify auto commit from within stored procedures. All right, question 5, another multi-select, and this one is about one of Snowflake's most exciting features. Question 5 is about secure data sharing, and honestly, this is one of those topics where Snowflake really differentiates itself. So let's make sure you understand it deeply, not just for the exam, but because you'll use this in real life. Here's the scenario. A Snowflake architect is building a data product. They want to expose data to consumer accounts using secure data sharing. They're writing a series of grant select statements trying to add various object types to a share: a standard view, a secure view, an external table, a dynamic table, and a stream. The question is, which of these grant statements will actually succeed? This is a multi-select, select all that apply. Your options are option A, dynamic table; option B, external table; option C, standard view; option D, stream; option E, secure view. Now think about which ones can actually be shared through Snowflake's secure data sharing mechanism. Pause the video here, think and choose the right answer. All right, the correct answers are A, B, and E. Let me walk you through each one. Option A is correct. Dynamic tables are shareable. Dynamic tables are Snowflake's declarative transformation feature. They're like materialized views, but with incremental refresh built in. Because they expose a defined governed result set, they can be included in a share and are explicitly supported. Option B is correct. External tables are shareable. An external table is a Snowflake object that points to files in external cloud storage, S3, Azure Blob, GCS, and exposes them as a queryable table. Because the access and schema are controlled by Snowflake's metadata layer, these can be shared with consumer accounts. Option E is correct. Secure views are shareable. In fact, the secure view is probably the most commonly used shareable object. The keyword is secure. When you create a view with the secure keyword, Snowflake hides the underlying query logic from the consumer. They can only see the result set. This is crucial for governance. You can share aggregated or masked data without exposing your underlying table structure or business logic. Now the two that are not shareable. Option C, standard views, are not shareable. You might be wondering, what's the difference? Isn't a view just a view? Here's the critical distinction. A standard view exposes its SQL definition to anyone who can access the view. If you shared a standard view, the consumer could potentially see your underlying query logic, your table names, even your data architecture. That's a governance risk Snowflake doesn't allow you to take through a share. Only secure views which hide that logic are eligible. Option D, streams are not shareable. Streams are account-specific change data capture objects. They track changes to a specific table within your account. They're inherently tied to the internal mechanics of your account's micropartitions and their offsets. They simply aren't designed for cross-account access and cannot be added to a share. So to summarize what is shareable: tables, secure views, secure materialized views, external tables, and dynamic tables. That's your list. Print it, stick it on the wall, whatever it takes. Let's keep rolling. Question 6. Okay, question 6 is a cost question. And if you've worked with Snowflake in production, you know that cost awareness is not optional. It's a core skill. This one is a multi-select as well. Here's the scenario. A Snowflake architect is reviewing 5 optimization features before enabling them on production tables. They've looked at the DDL for each one, and they want to know which of these will add storage costs to the account's bill. And the options are: option A, multi-cluster warehouse; option B, search optimization; option C, materialized views; option D, table clustering; option E, query acceleration service. Which ones hit your storage budget, not just your compute budget? Pause the video here. Think and choose the right answer. This is a multi-select, and the correct answers are B, C, and D. Let me explain why, starting with the 3 that do add storage costs. Option B, search optimization, is correct. When you run alter table, sum table, add search optimization, Snowflake builds and maintains a set of persistent auxiliary data structures, essentially access paths, that live on storage. These structures make point lookup queries dramatically faster, but they come at the cost of additional storage. They have to be stored somewhere, and that somewhere is your Snowflake account's storage. Option C, materialized views, is correct. A materialized view is literally a copy of the query result set written to storage and kept fresh through automatic background refresh. Because you're persisting those query results as physical data on Snowflake's storage layer, your storage consumption goes up. How much depends on the size of the result set, but it's measurable. Option D, table clustering, is correct, and this one surprises people sometimes. You might think it's just reorganizing existing data. How does that add storage? Here's the thing. Snowflake maintains additional metadata files to track the clustering information across micropartitions. It may also need to reorganize some micropartitions during the reclustering process, which can temporarily or permanently increase the number of micropartition files. Both of those things add to your storage footprint. Now, the 2 that do not add storage costs. Option A, multi-cluster warehouse, is a pure compute feature. Adding more clusters to a warehouse means Snowflake spins up additional virtual compute nodes when concurrency demand is high. Those nodes consume compute credits, not storage. No data is being written anywhere, so A is incorrect. Option E, query acceleration service, is similarly a pure compute feature. It offloads parts of large scan queries to a shared pool of compute resources managed by Snowflake. Again, nothing is being stored. Credits are consumed, not storage bytes. So E is also incorrect. You might be wondering, why does this distinction matter so much? Because compute costs and storage costs are billed completely differently in Snowflake. Compute costs are time-based and usage-based. Storage costs are monthly and accumulate silently. If you enable search optimization or materialized views on a huge table and forget about it, your storage bill can creep up significantly over time. Architects need to consciously account for both dimensions before enabling these features. Question 7 is coming up, and it's a security question, always a crowd favorite on exams. All right, let's look into question 7, and this one is about multi-factor authentication with SnowSQL. It sounds very specific, but it's the kind of detail that separates someone who's actually configured Snowflake environments from someone who's just read about it. Here's the scenario. A Snowflake administrator is configuring SnowSQL access for a team of analysts. They've enabled multi-factor authentication, and they're using a specific flag, MFA-passcode-in password. They've set this in the SnowSQL config file, and they're connecting with SnowSQL-C prod. The MFA token from Duo at the moment of login is 482917, and the user account password is secret-pass. When the password prompt appears, what should the user type? Your 4 options. Option A, 482917, secret pass. Secret pass. That's the passcode, then a pipe delimiter, then the password. Option B, 482917, just the passcode alone. Option C, secret pass, just the password alone. Option D, secret pass 482917, the password immediately followed by the passcode with no separator at all. What do you think? Pause the video here. Think and choose the right answer. The correct answer is option D. secret-pass.482917. Password first, passcode immediately after, no separator. You might be wondering why that's the format. Let me explain what's actually happening under the hood. When you enable MFA passcode in password in SnowSQL, you're telling the Snowflake authentication system, I'm going to embed my MFA token directly in the password field as a convenience. Snowflake then knows to split the credential internally. The format is always primary password first, MFA token appended directly after with absolutely no separator between them. This design exists to support automated CLI workflows where you don't want an interactive MFA prompt breaking your script. You can pre-compute the current token and concatenate it into the password field programmatically. So why are the other options wrong? Option A uses a pipe delimiter. No separator of any kind is supported. Whether you use a pipe, a dash, a space, a comma, any character between the password and the passcode will cause authentication to fail entirely. Snowflake doesn't look for a delimiter. It uses internal logic to determine where the password ends and the token begins based on the expected token length. Option B is just the passcode. That's missing the primary password entirely. Snowflake needs both components. Without the password, authentication is rejected. Option C is just the password. That's missing the MFA token. With MFA passcode-in password enabled, the system expects the token to be present. Without it, authentication fails. This is one of those exam questions where the detail really matters. The format is password then passcode, concatenated, no separator. Burn that into memory. Let's go to question 8. Question 8 is about database cloning in Snowflake and what happens to tasks when you clone a database. This is a really practical question because a lot of teams use cloning to create dev and test environments. And this is exactly the kind of gotcha that bites people when they first do it. The scenario, a DevOps team clones their production database to create a testing environment. They run create database prod db clone prod db. After the clone completes, they run show tasks in database prod db clone and see that the ETL task is there. The definition, the schedule, everything is copied, but the state shows suspended. The task is not running, even though the same task in the source database is still running fine. The question is, what is the primary reason clone tasks stop running after a database clone? Your 4 options. Option A, clone tasks lose their privilege grants during the clone operation. Option B, tasks cannot be included in a database or schema clone. Option C, Clone tasks are automatically suspended by Snowflake to prevent duplicate execution. Option D, object references in the task body become invalid after cloning. What's your answer? Pause the video here, think and choose the right answer. The correct answer is option C. Snowflake intentionally suspends all tasks in a cloned database by default. And when you think about it, this actually makes total sense. Think about what would happen if cloned tasks kept running. You'd have two instances of the same ETL job running, one in production and one in your clone, both writing to their respective tables. In a dev or test environment, that might be fine. But what if your task is writing to a shared table or sending notifications or triggering downstream processes? Duplicate execution could corrupt your data or cause serious operational issues. Snowflake protects you by defaulting clone tasks to suspended. It's a deliberate safety mechanism, not a bug or an oversight. When you're ready to run tasks in the clone, after you've validated your environment, you simply issue alter task proddb clone.public.etl core task resume. You're in control of when it starts. Now, why are the other options wrong? Option A says privilege grants are lost. That's incorrect. Privilege grants are fully preserved during cloning. The clone task retains its ownership grant and any other privileges it had. Privilege loss, not the reason it's suspended. Option B says tasks cannot be included in a clone. That's also incorrect, and the show tasks output in the question literally proves it. The task is there, it's just suspended. Tasks are cloned along with all other objects when you clone a database or schema. Option D says object references become invalid. This is a reasonable sounding guess because you might think the task body references tables by name and those names changed. But here's the thing. The clone task references objects within the clone database, and those objects exist. The references are valid. The task is suspended for a different reason entirely. So the takeaway, when you clone a database or schema, always remember to check your tasks and resume them deliberately after you've confirmed the environment is ready. Don't assume they'll start on their own. Question 9 is all about cost governance. Let's go. Question 9 is another cost management scenario, and this is one of those architect decisions type questions that shows up frequently in the certification. Here's the situation. A Snowflake architect is managing an analyst virtual warehouse called Analyst WH. The warehouse is a medium size, has auto suspend set to 300 seconds, auto resume is on, and the statement timeout is 3,600 seconds, 1 hour. The architect looks at the billing dashboard and sees that credits consumed this month are 8,420. The budget was 500, 8,420 versus a budget of 500. Yeah, that's a problem. The architect needs a feature that will send an alert at 80% of the budget and automatically suspend the warehouse when 100% of the budget is reached. What feature does this? Your options. Option A, auto suspend setting on the warehouse. Option B, multi-cluster warehouse scaling. Option C, resource monitor. Option D, query timeout parameter, statement timeout in seconds. Take your pick. Pause the video here. Think and choose the right answer. The correct answer is option C, Resource Monitor. And I want to be really clear about why each of the other options fails, because this question is specifically designed to test whether you know the difference between features that seem like they control costs and the one that actually enforces a budget. Let's start with option A, Auto Suspend. Auto Suspend is genuinely useful. It stops a warehouse from burning credits when nobody's using it. If the warehouse is idle for 5 minutes, it pauses. That saves money on idle time. But here's the critical limitation. Auto Suspend only kicks in when the warehouse is idle. The moment someone submits a query, the warehouse resumes and starts consuming credits again. If analysts are running expensive queries all day long, Auto Suspend does absolutely nothing to cap that spend. It cannot enforce a budget. Incorrect. Option B, multi-cluster warehouse, is almost the opposite of what we want. Adding more clusters to a warehouse improves throughput and concurrency, which is great for performance, but it means more credits being consumed in parallel, not fewer. Enabling multi-cluster scaling when you have a runaway cost problem would make the problem worse, not better. Incorrect. Option D, statement timeout in seconds. This one is actually a useful tool, but for a different problem. A query timeout cancels any individual query that runs longer than the specified duration, in this case 1 hour. That prevents single runaway queries from hogging resources forever, but it doesn't cap total credit consumption. Even if every query finishes in under an hour, you could still rack up thousands of credits if enough queries run. This doesn't solve the budget problem. Incorrect. That leaves option C, the resource monitor, and this is the one Snowflake feature purpose-built for credit governance. A resource monitor lets you define a credit quota, say 500 credits per month. You then set thresholds. At 75%, send an email notification. At 100%, suspend the warehouse. You assign the resource monitor to the warehouse, and it enforces those limits automatically. That is exactly what the architect needs. Create the resource monitor, set the quota to 500, configure the alert and suspend triggers, assign it to analyst quote H, and you're protected. The lesson: if the question is asking about enforcing a hard spending limit on a Snowflake warehouse, the answer is always resource monitor. Nothing else in Snowflake does that. All right, we're on the home stretch. Question 10. Let's finish strong. Question 10 is about the search optimization service, and this is a performance optimization topic that the exam tests in a really nuanced way. The question is designed to see if you understand not just what search optimization does, but when to use it and what makes it effective. The scenario Snowflake architect is evaluating whether to enable search optimization on a table called customer events, which has 250 million rows. They've pulled the column statistics. The customer ID column has 45 million distinct values. That's high cardinality. The session ID column has 30 million distinct values, also high cardinality. The event type column has 12 distinct values, low cardinality. And the region column has 8 distinct values, also low cardinality. The dominant query pattern is a point lookup. Select event details from customer events, where customer ID equals a specific value. The architect plans to run alter table customer events, add search optimization on equality of customer ID. The question asks, what is the key consideration when enabling search optimization service? Your 4 options. Option A, search optimization only applies to external tables. Option B, the target column should have high cardinality, around 100,000 or more distinct values. Option C, the table must already be clustered before enabling search optimization. Option D, search optimization is most effective on low cardinality columns. What's your answer? Pause the video here. Think and choose the right answer. The correct answer is option B. Target columns should have high cardinality, ideally 100,000 or more distinct values. Let me explain the full picture here, because understanding this deeply will help you both on the exam and in real-world architecture decisions. When you query a table in Snowflake, the normal pruning mechanism kicks in. Snowflake looks at the metadata for each micropartition, the min and max values for each column, and skips partitions that can't possibly contain your search value. For low cardinality columns like region with 8 distinct values, this pruning works beautifully. Every micropartition probably contains all 8 regions, so pruning doesn't help much. But the table is small enough in those dimensions that queries are still fast. But for a column like customer ID with 45 million distinct values across 250 million rows, the standard min-max pruning becomes less effective. Each micropartition might have customer IDs ranging from 1 to 45 million, so Snowflake can't skip many partitions. You end up scanning a lot of data just to find one customer's records. That's exactly where Search Optimization Service steps in. It builds persistent auxiliary data structures. Think of them as highly efficient lookup indexes that tell Snowflake exactly which micropartitions contain a specific customer ID. Instead of scanning thousands of micropartitions, Snowflake jumps straight to the handful that matter. The query that was scanning for minutes now returns in seconds. But this only works when the column has enough distinct values to make those lookup structures meaningful. The Snowflake guidance is approximately 100,000 or more distinct values. Customer ID with 45 million distinct values, perfect candidate. Event type with 12 distinct values, not worth it at all. Now let's quickly validate why the other options are wrong. Option A says it only applies to external tables. That's completely backwards. Search optimization applies to internal tables. External tables are not eligible. Incorrect. Option C says the table must already be clustered. This is a common misconception. People think search optimization and clustering are related features that work together as prerequisites. They're not. They're independent features that address different problems. Clustering helps range-based queries on sorted columns. Search optimization helps point lookups on high cardinality columns. You can use one, both, or neither. No dependency between them. Incorrect. Option D says it's most effective on low cardinality columns. This is the opposite of the truth. Low cardinality columns benefit from clustering, not search optimization. For 8 values like region, Snowflake's standard pruning can already handle it efficiently. Search optimization on a low cardinality column would cost you storage without delivering meaningful performance gain. Incorrect. So the bottom line for question 10, search optimization is for high cardinality columns used in point lookups on large internal tables. Evaluate your column statistics, check your dominant query patterns, then make the call. And that brings us to the end of all 10 questions. Can you believe we just covered 10 exam level topics in one go? Let me give you a quick rundown of everything we covered, because this is actually your study summary right here. Question 1, Kafka ingestion. Records land in Snowflake as variant data in a single column called record content. Metadata goes to record metadata. Schema on read, not schema on write. Parsing is done downstream with SQL. Question 2, internal stage file retrieval. When you need to recover files from an internal named stage, the get command via SnowSQL is your lowest overhead option. The web UI can't do it, the REST API is overkill, and a Python script adds unnecessary complexity. Question 3, temporary table lifecycle. Temporary tables are session scoped. They auto-drop when the session ends. No time travel, no failsafe, no conversion to other table types. Great for scratch data, not for anything that needs to survive a session. Question 4, Snowflake transactions. DDL always triggers an implicit commit. This is the big rule. Begin work and commit work are valid aliases. Auto commit cannot be changed inside stored procedures. DDL inside explicit transactions is not safe. Question 5, secure data sharing. Shareable objects include tables, secure views, external tables, dynamic tables, and secure materialized views. Standard views and streams cannot be shared. The secure keyword on a view is what makes it eligible. Question 6, optimization feature costs. Search optimization, materialized views, and table clustering all incur additional storage costs. Multi-cluster warehouses and query acceleration service are pure compute costs only. Question 7. MFA with SnowSQL. When MFA passcode and password is enabled, the correct format is password concatenated directly with the MFA token. No separator, no delimiter, password first, then token. Question 8. Task behavior after cloning. When you clone a database, all tasks in the clone are automatically suspended by Snowflake to prevent duplicate execution. Privileges and references are preserved. You must manually resume tasks when ready. Question 9. Cost governance. Resource monitors are the only Snowflake feature that enforces a hard credit spending limit. Auto-suspend, query timeouts, and multi-cluster scaling each solve different problems. Only a resource monitor can alert and suspend a warehouse at defined credit thresholds. Question 10. Search optimization service, most effective on high cardinality columns with 100,000 or more distinct values, does not require clustering as a prerequisite. Applies to internal tables only, not external. Low cardinality columns are not a good use case. That is a genuinely solid foundation for the SnowPro Core Exam, and honestly for working as a Snowflake data engineer or architect in the real world. Now here's the thing I want to leave you with. The SnowPro Core Exam is not trying to trick you. It's testing whether you understand how Snowflake actually works, not just whether you can memorize facts. And the best way to cement this knowledge is to go hands-on. Open up a Snowflake trial account, spin up a warehouse, create some temp tables, set up a Kafka connector if you can, configure a resource monitor, play with these features, and watch what happens. That hands-on experience is worth 100 flashcard sessions. If you found this video helpful, please do hit that like button. It genuinely helps more people find this content who are on the same certification journey as you. Subscribe if you haven't already, because we've got more SnowPro Core content coming, covering everything from virtual warehouses and caching to security policies and data governance. Drop your questions in the comments below. If there's a topic you want us to dig deeper on, transactions, data sharing, cost management, whatever it is, let me know and I'll make sure we cover it. You've got this. Good luck out there, keep studying, and I'll see you in the next one.